In that section that we just looked at, we see how we can actually measure the voltage of a particular pairing of redox partner, right? So you have zinc and copper, we get 1.1 volts in this case. Now, of course, our goal is if we want to design, let's say, a battery, we want to know what is the voltage of the battery that we're going to get, right? Because the higher the voltage, the more work it could do. But of course, you don't want to have so high a voltage that would actually damage the equipment. So there's sort of different considerations there. But the key point here is that you want to know how much voltage you're going to get when, let's say, you're going to pair, I don't know, something like silver and copper. Would it even work, right? And so you don't want to have to do an experiment every time. You could do the experiment. You can connect, you can say put silver on this side instead of zinc and copper, and you can see the voltage, but it'll be kind of cumbersome if you have to do this every time, right? So is there a way to do this non-experimentally, just by doing calculation on paper and figure out what voltage we're going to get? Well, we know that we can get this E cell by doing this calculation, right? Which is the potential of the cathode minus the potential of the anode. The problem is we don't really know what these individual numbers are. What we know is this. We can measure the E cell, which is the delta, the difference between the two sides, but we can't measure the individual sides, okay? Which is kind of different compared to that analogy I've been giving you with water. With water, we can measure the height of individual sides. So we can say, okay, let's make that 0, and I can measure the height on this side. And if I make this 0, I can measure the height on this side. Then I can measure the delta, which is just the difference of the two heights. The problem here in the cell potential is there is no 0 that's defined, okay? And that's why we can't really measure the cell potential of just the one electrode and the cell potential of the other electrode. We can only measure the difference of the two. But let's think about that again, right? All we need to do is really just define something that has 0 volts. The same way as we define that the bottom of this tube right here is 0 height, height equals 0 meters, for example, right? So once we define it that way, then everything else is measured relative to that. That's exactly what we do also in the case of electrochemistry. And this is something that you've seen done before in other parts of chemistry, hopefully. When we try to calculate enthalpy of formation, when we calculate a certain absolute entropy, we define something that is 0, and that's arbitrary. Just pick something that everybody agrees to be 0, and then everything else is measured relative to that, right? So same idea here. We're defining an electrode that we would say have 0 volts when we measure it. So which electrode should we use? It's arbitrary, but you want something that's pretty easy to set up, right? Experimentally. So in this case, we choose something called a hydrogen electrode, and specifically the electrode looks like this. You have an acid solution in here at 1 molar H plus, okay, so it has 1 molar H plus, and then you have hydrogen gas in here in equilibrium with the acid, and that one has a pressure of 1 atm. Since both hydrogen gas and acid are not solid, they can't conduct electrons, so we need an electrode, an inactive electrode in this case, so we choose platinum as the inactive electrode, okay? And then what you want to do is that this particular electrode is defined as having 0 volts for its own cell potential. So this is what we call a half cell potential because it's only 1/2 of a pair, right? You're going to connect this guy to some other electrode that you're interested in studying, and then whatever voltage you read, you would say that's the half cell potential of that new electrode, that other one that you're pairing with the standard hydrogen electrode. Shorten it as SHE in this case. Basically, the reactions are given right here. So the oxidation reaction is shown at the bottom here, which is hydrogen going to 2H plus 2 electron. So in this case, we would say that the oxidation half cell potential is 0. Again, I say half cell because this is only 1/2 of a full cell, right? And then the reduction potential would be just the reverse reaction, the 2H plus 2 electrons going to H2. That reduction half cell potential is also going to be 0 volts. I put in the actual pressure and concentration here to indicate that this is done under standard condition. Remember, standard condition requires that all gas pressures equal 1 atm, all molarity or concentration of aqueous solution equal 1 molar. Okay, now, so how do I use this thing? I'm going to take this and combine it with electrode of interest. Let's call it X in this case. So I'm going to run a reaction, a redox reaction, where either X is oxidized and my standard hydrogen electrode is reduced, or vice versa. And then what I'm going to do is then I'm going to look at the voltage that shows up here. Okay, so again, replacing one of these with the standard hydrogen electrode. Whatever voltage that shows up there should be the potential corresponding to that other electrode that I'm pairing up with the standard hydrogen electrode, right? So hopefully that makes sense. So here's two examples, one with the zinc and the other one with the copper. So again, we have used this zinc copper example for quite a bit, so I want to continue with it now with the standard hydrogen electrode. So here, if you see, I put my zinc anode on the left side, and I put my standard hydrogen electrode, my SHE, on the right side. And when I connect that and I put a voltmeter in between, I see a number, and that number is 0.76 volts. So that tells me that zinc spontaneously donates electron to the standard hydrogen electrode, and that zinc has a half cell potential of 0.76. Zinc is in the anode. In this case, zinc is undergoing an oxidation, and then the standard hydrogen electrode is undergoing a reduction. Now, let me try this out with the copper. If I pair this up with the copper, actually the opposite happens. The standard hydrogen electrode now, even though it's located on the same side, actually electron now is flowing out from the standard hydrogen electrode to copper. So again, what does that tell you? That tells you, you might want to, what should go on in your head right now is to think about the fact that if you have this same setup, right? Let's say the standard hydrogen electrode is there. So zinc must have a higher level compared to the standard hydrogen electrode. But then when we pair this up with copper, hydrogen electrode is still there, but copper must have a lower potential than the standard hydrogen electrode. So then the flow goes this way if it's copper, and then if it's zinc, the flow is this way. Okay, so keep that in mind as an idea, okay, conceptually. So now again, when we do this with the copper with standard hydrogen electrode, the flow of the electron goes from the SHE to the copper, and we see that voltage is plus 0.34. Okay, so again, with zinc, the flow is from zinc to the hydrogen electrode. With copper, the flow is from the hydrogen to the copper, okay? Now, it's kind of confusing, right? If we have to do this, we have to kind of keep track of who's flowing out which way, okay? It's going to be kind of confusing if I have to remember that, okay, when it's paired up with zinc, the electron goes from zinc to the hydrogen, but then when it's paired up with copper, the electron flows out from the hydrogen to the copper. I want just one way of remembering things. So in order to make it consistent, when we put this number in a table, we always place the standard hydrogen electrode on the anode side. So in other words, every number is measured as if the hydrogen electrode is the anode. Okay, so with respect to the copper, that's pretty easy because that's already the anode right here, right? So, I mean, the electron is flowing out from the standard hydrogen electrode, so therefore that side is the anode, so this side is the cathode. So that means the number we got, which is 0.34 volts, that measures the half cell potential of the copper here in a reduction reaction. So that number that we got is what we call the reduction half cell potential, okay? And it has a symbol. The symbol is E red, with a standard degree symbol at the top there. So that just means the reduction half cell potential. Okay, so for copper, this is 0.34 volts. For zinc earlier, when we do the reaction, the zinc serves as the anode. But now, again, we want to make it consistent. We want to say that the hydrogen electrode should always be the anode. So if I want to assume that the hydrogen electrode is the anode, and I want to think about, well, how will the voltage be when the electron is flowing the opposite way? Then the only change there is that the voltage will be negative 0.76 volts. Again, negative voltage is not really spontaneous, but we're trying to make a table here where we can rank zinc, copper, and hydrogen together and have those values tell us something, right? So in this case, we would say the E reduction of zinc 2 plus, because again, we're thinking about a reduction, right? Because the zinc is now going to be placed on the cathode side. This is going to be negative 0.76 volts, okay? So hopefully that makes sense. I want to just summarize it again here. We're trying to use the hydrogen electrode, which is our standard electrode, as a way to determine the half cell potential of other metals, other species, right? So we're going to create these electrochemical cells, these voltaic cells, with the hydrogen electrode on one side and with the other electrode on the other side. To make it consistent, we always put our hydrogen electrode on the anode side. So therefore, what we get, the numbers we get, is basically the unknown electrode reduction reaction for it, since it's going to be placed on the cathode side, and it's going to be the cathode, but that's also the same as the E cell. If we do this for copper earlier, we see a spontaneous flow from the hydrogen electrode to copper, which means the hydrogen electrode is on the anode, the copper is on the cathode, and the number we get is positive 0.34 volts. So that corresponds to this reaction, the reduction of copper, okay? So that's 0.34 volts. If you do it for zinc, what we see is the opposite flow. The zinc is the anode, hydrogen electrode is the cathode. But to make it consistent, we want to imagine as if the hydrogen electrode is the anode. So if the hydrogen electrode is the anode, then that number should be negative 0.76. So we're really measuring the reduction potential of zinc 2 plus going to zinc, and that's negative 0.76. If we put all of these together in a table, it will look something like this. This side just shows you what the reduction half reaction looks like for each of those species that we just talked about. So this is zinc 2 plus, this is the H plus in the standard electrode, and then this is the copper 2 plus. Again, they're all reduction reaction, very important to keep in mind here. And then this is the half cell potential that we just measure, which is given the symbol E, standard red. And for zinc is negative 0.76, for the standard electrode is 0, and for copper is positive 0.34. Okay, now once you have this number, how useful are these numbers? Again, the point of developing this is so that we can just calculate a particular pairing that we're interested in instead of having to do an experiment. So let's say I'm interested in pairing zinc and copper, okay? How would I pair them to give me a voltage, right? Well, remember that I can calculate my voltage of any cell by taking cathode minus anode, right? Okay, so what I have to think about here is that, well, let's say I want my zinc to be in the cathode, okay? Let's say cathode is zinc and anode is copper. Would I get a functioning cell or not? Well, if the cathode is zinc, that means the E cathode is going to be negative 0.76 minus the E anode. Well, the E anode, if it's copper, it's going to be 0.34 volts. So when you add these two things together, negative 0.76, negative 0.34, you get negative 1.1 volts. But it's negative, so it doesn't work, right? Because remember, what we learned earlier is that spontaneous flow must always give you an E cell that is positive. That means that this is to make the zinc as a cathode and to make the copper as the anode will not work. It's not going to be spontaneous. So what would be spontaneous? Well, all we need to do is flip them. We need to make the zinc the anode and the copper the cathode. If we do that, look at this. If the cathode is copper and the anode is zinc, copper has a potential of plus 0.34 minus the zinc cell potential of negative 0.76. So when you add them together, you get positive 1.1 volts, which means that this is going to be spontaneous. So the idea here is that if I want to make a battery out of zinc and copper, the zinc has to serve as my anode, the copper has to serve as my cathode. Okay, does that make sense? So hopefully that clears up the idea of how to use these numbers. There's another way to do this. Another way to do this is to kind of write the reaction in the opposite way, which is to write the reduction half reaction and then the oxidation half reaction. So in this case, if I want my copper to be on the cathode side, that means it's going to undergo reduction, right? Because that's what cathodes do. And so I'll just write it this way. And the E reduction is just going to be positive 0.34. We already know that. That was the number that we got earlier, right? This is all for reduction. If my copper is being reduced, that means my zinc has to be oxidized. So I'm going to write an oxidation reaction here. Now, the number we got earlier, the negative 0.76, is for a reduction reaction. So if you want a zinc to be oxidized, that means its oxidation potential is going to be positive 0.76. Our E cell in this case would just be the E reduction plus the E oxidation, and that's going to be 1.1 volts. So you see that we get the same exact answer either way, but both of those answers tell us that zinc has to be oxidized, it has to be on the anode, copper has to be reduced, it has to be on the cathode, okay? So whether you use this method of calculating the E cell or this method of calculating the E cell, is the same. You just need to know that in one case, you're just using this formula and just thinking about who wants to be on the cathode, who wants to be on the anode, and then just using the numbers that you have from the half cell potential directly. But if you want to actually write out the reaction the way I did it here, you have to flip one of those reactions, which means you have to take the negative of the number that you're given to get the E oxidation. Okay, we'll do more of these problems later on, but that's just a preview of what you'll be doing in the future. Now, once we have the E reduction for a couple of these guys, right, copper and zinc, we can start measuring all other ones. We can measure them relative to the standard potential, or we can measure them relative to one of the ones that already exists, right? So for example, let's say I'm interested in figuring out a bromine electrode, right? Which is just bromine being converted to bromide. So in this case, that's the reduction. I can just pair it up with zinc. I know zinc is pretty good at donating electron. So I pair it up with this bromine, I get a voltage of 1.83. That allows me to calculate the E cell for just bromine alone. Since I already know that the E cell for zinc is negative 0.76, again, E cell is E cathode minus E anode. The cathode here is my bromine. The anode is my zinc. It's negative minus 0.76. The whole thing is supposed to equal to 1.83. So then solving for the EBR2, I get EBR2 equals to 1.07 volts. So again, that's telling me that the reaction for Br2, where Br2 is being reduced, right, going to Br minus plus 2 electrons right here, that has an E cell of 1.07 volts. And again, I can take this and then use it to measure something else. So that's the example here. I use it to measure this vanadium ion cell potential. I'm able to find that number from that comparison with Br2, okay? I would just point out that as we're measuring all these half cell potential values, they are all tabulated. You can find this in various sources, either different textbooks. The one that I'm linking for you here is the one from the University of Rhode Island, which has an extensive list of all of these half cell potentials. They're going to be useful later on as we're doing some calculations. So if you click on that link in your lecture notes, you will see that it will take you to this page. And as you can see, what this page is showing you is the half cell potential, again, for reduction. Okay, so keep in mind that this is for reduction reaction, and it goes from very positive on the top all the way to very negative at the bottom, right? And they split it conveniently for you for acidic conditions on the top, and right here in the middle, you can see that there is a split, and then we go to a basic solution right here, and then we start again from positive to negative, okay? So we're gonna use these numbers with different problems that we're looking at, because that will help us calculate the E cell for any kind of pairing we want.